Alright, okay. Assalamualaikum warahmatullahi taala wabarakatuh. Um, so nak confirm sekali lagi boleh nampak muka dan boleh dengar suara dengan jelas Alright. And boleh nampak slide juga. Spatial Epidemiology slide show bukan slide yang presenter view Okay. Right. So tak nak bertukar pula. Okay. Baru keluar Professor in Epidemiology and Statistics. So, baru edit kan, baru edit. Okay. Alright. So the
Prof, sorry, ada
objective
recording ke?
ada. Tengah record tu.
Oh, alright.
Alright. So the objective of the lecture is number one to understand um, basic concept lah of spatial epidemiology. Number two, to understand types of spatial data format. Number three, to understand coordinate reference system. Number four, to understand types of spatial data analysis. So all of the objectives are basically to understand lah, So there is no need to know how to perform spatial data analysis. But if you have any problem, you can always go to Afiq or Hazlino lah. Both of them can do well, spatial data analysis. At least for point pattern analysis. So a little bit of background of spatial epidemiology. We know that epidemiology is the study, either scientific, systematic, or data-driven, of the distribution, meaning that frequency or pattern of diseases and determinants, the causes, the risk factors of health-related states and events, not just diseases, all right? So that includes risk factors and disabilities, so on and so forth. So in specified populations in the neighborhood, school, city, state, country, global, and the application of the study to control the health problems. So that is basically the definition of epidemiology. And spatial means things related to the position, area, and size of things. So we are using information from position, from area, and also the size of the matters related to epidemiology, right? Spatial epidemiology also means describing and analyzing geographic variations in diseases. But again, we just mentioned kan, epidemiology is not confined to diseases. It also related to health events, not just diseases. So by looking at or by describing and analyzing geographic variations, we try to understand the relationship between the geography or the locations with demography, with environment, with behavioral, with socioeconomy, with genetics, with some risk factors, for example, infectious risk factors. So if we have information on the variations of disease based on locations, So if we see that in Guamusang there are many more malaria cases, what are the factors related to that, or what are the factors contributing to more malaria cases in Guamusang? And using that information, we can devise policies and control and prevention program. If we look at the For example, certain areas with high incidence of cancer, for example, why those areas or those locations have higher or more patients with cancers? Is it because there are more people there, or is it because there are risk factors in the area? For example, some carcinogens or some other factors that may contribute or maybe risk factors for cancer in those areas. Okay, but to know that to be able to do that, we have to have information about the geography or the locations of the disease of interest or the health of interest. So so when we say we need information of the locations or the geography, um, there are three common types of spatial data that we can use as the basis of the locations. For example, we can use the um, the point data dot dot dot. For example, we can have the points of dengue cases. We can have the points of HFMD cases, the points of leptospirosis cases. So those points can correspond to the locations of the residence of the patients. They can also be the locations of the occupations, or maybe the locations of where they receive treatment, so on and so forth. So so again, but we have points. So this usually, uh, how we get this point. Usually we geocode. We go and tag the locations of the patients. So we go to their house and then we tag. So how we tag? We can use GPS device, Garmin, for example, that can cost around a few hundred ringgit or a few thousand ringgit, or you can simply use your phone. But your phone is less accurate compared to GPS. And then we can have line string. This is special data that you know that are related to, for example, uh, roads, jalan, or railways, or sungai, rivers, you know. So because they can form lines, and we can have data in the form of polygons. So, for example, um, district, daerah, jajahan, mukim, or state, or country. Or for example, we can have also, and also we can have like building. If the building is huge, kan. So the boundary of the building can also be polygon. And then we can have a collections of those three data lah. We can have point, line, string, polygons in the same spatial data. So right. So um, if you have points for dengue, points for HFMD, points for leptospirosis in the same map, then you can call that as multi-points data. If we have data for roads, for rivers, for railway tracks in the same map, that is, so we call that as multi-string data, right? And we actually there's one more lah, tapi not commonly used, which is the volume data. So this is the raster data. For example, the density of rain, the temperature pattern, the um, pollution index. For example, what we call that? Apa tu? Yang 2.5 PM, PM10, PM2.5, you know. So those are raster data. Okay, and then we also heard we have heard about GIS, right? Geographic Information System. So what? So are they different? GIS and spatial epidemiology, are they two different things? I think yeah, there are similarities, but they are not the same, right? GIS is not spatial epidemiology. Spatial epidemiology is not GIS, right? Because GIS is a computer system or a system that contain informations about the geography. So GIS system captures, store, check, and also display data related to position on on Earth surface, for example lah. Okay, for Earth on Earth surface. So again, it captures, it store, it check, it display. So it is an information system. So GIS can show many different kinds of data, streets, building, vegetation, so on and so forth. Um, so if you have GIS, you will be able to, to convert your your data into something that people can see. Okay, so they can see in map, you know. For example, like Google Map lah, Google Map. So that is Google Map itself. Google Map itself is not a GIS, but the system too. The system is GIS. But spatial epidemiology is about position, area, size of things related to the epidemiology of certain diseases or certain health-related states. Again, this data, the point, the line string, the polygons are basically known as vector data. Okay, vector data. There is another type of data we call as raster data, which is like inilah data yang volume is continuous. For example, density of rain, vegetation index, uh, PM10, PM2.5, where there is no point. You will see like a continuous uh, type of spatial data. So that is raster data. And triangular irregular network, which we it's quite complicated concept, but when you do spatial epidemiology, sometimes you might be using triangular irregular network in the analysis. So this is one example of this is a map, right? This is a map. This is not GIS. Okay, GIS again is a system. So if you are only doing data analysis, getting data, and then getting spatial data, and then analyze, and then you make report. So I think you are doing more spatial epidemiology than GIS. Okay, GIS person is someone who's handling the geography data. It means that they store it in the server. they manipulate the data in the server, and then they convert that into maps, for example, right? But they don't usually analyze the data. They just manage the data, usually lah, usually. All right. For spatial epidemiologists, we have that spatial data. We analyze, trying to understand the relationship between the coordinates and also the factors. So in the map there, you can see lines, basically represent highways. You have points represent locations of certain things, and then you have polygons. For example, in that case kan bangunan ke apa kan. So we have points, we have lines, we have polygons, and we also have raster. For raster, for example, if you look in the map there, it can be the vegetation index, can be the elevation, ketinggian, elevation. It can be density of rain, you know, or distribution of PM10 or PM2.5. Those are raster data. So again, when you want to understand what kind of data that are related to spatial, these are the data. Okay, one is the vector data. In vector data, you have lines, string, points, and polygons. And then you have raster data, and then you have thin data, triangulated irregular network, and then usually you also have attribute table. For example, for if you have a point and a point coordinates for patient A, usually you also have the gender of the patient, the age of the patient. You also know the comorbidity of the patient. You also know the outcome of the disease. So that is basically information related to the point. Okay. Right. So again, spatial data, you have a feature class. Feature in spatial in GIS, they sometimes they call I mean they don't call variables. They call that as feature class. Okay, feature class. So ini macam dalam machine learning lah, dalam computer science. They don't call variables. We call variables, but they call variables or columns as feature class. And then inside the class though, there are attributes. For example, feature class is gender, attributes is male and female. Feature class is weight, attributes is kilogram. For example, the weight of person. So I'm not sure why, but that's how. So if you work with ArcGIS or QGIS, they don't usually call as variable, but they call as feature class. And the values of the variable they call as attributes. Right. So data collection and management. So you need to capture, verify, and do some structuring process. All right. You need spatial reference frame. This is sometimes confusing, but we will go to that later. But for now, remember this as spatial reference frame. Right. So this spatial reference frame is provided by the coordinate reference system. Coordinate reference system. Because why? Because Earth is not a perfect sphere. Earth ni, bumi ni dia bukan bulat. Sebulat-bulatnya. Okay. It's not it's not a perfect sphere. Dia ada apa ni, dekat atas tu dia ada ketinggian kan, ada bukit, ada gunung semua kan. So it's not really sphere lah, right? It's not like bola bowling tu kan, licin je kan. right? It's not like that. So, so when you have the, Earth, which is a sphere, so you have like from west to east, from north to south. So we call this as northing or easting. Okay, northing or easting. So 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 if you point to somewhere, like for example, 20-degree longitude and 55-degree north, for example, like, so you can point dot dekat situ kan, right? So the Earth is round, okay. And now the problem is that when I want to show in the computer, or if I want to show on the textbook, I can give bawa bulat macam ni kan. So because you have to flatten Earth onto your computer screen or onto the book, so it become flat. So you imagine dulu kan kita ada, kalau kita ingatlah masa kita kecil tu kan, ada bola yang globe yang besar, yang bulat, yang lembik-lembik, kita tube tu kan. Ingat tak? Ada tak you all main? Mungkin tak ada kot. So macam mana, how would you cut that sphere so that you can put nicely on a flat surface? It's very difficult. So because of that, some people use this cutting, some people use that cutting, some people use different cutting. So that's why you see, you know, different cutting like this. All right. So this is like Mercator, Gold Peters. Mercator use this kind of projection. Gold Peters use this kind of projection. Apa tu? Gudu, Homolysin, Watermelon pun ada juga. Albers and Robinson. So they need to cut, you know. So you can imagine, right? So projection or map projection is the process of transforming Earth that is sphere into flat surface. Okay. Kan macam you tengok GPS kan, you tengok dalam kereta kan. When you set your Waze or Google Map, right? So the map tu is on your phone, flat, right? Tapi it is not flat actually kan, because it's like, unless you are a flat earth punya person lah, You know. So you memang golongan orang-orang yang beranggapan bahawa bumi ini flat, that is different lah kan. Tapi for majority of us, we think that earth is not flat, it's sphere. So macam mana, how can we project the map from sphere to flat? So there are various map projection system. Okay. So again, the map projection is a process of transforming the Earth from sphere to a flat piece of paper or computer screen. Things like that, lah. Right. That's number one. Number two, we also have coordinate reference system. Okay, coordinate reference system. Um, the So because you have different people propose different method for map projections, that's why there are different coordinate reference system. Because this coordinate reference system shows how you will project from this to this, and this coordinate reference system shows the projection for this guy, and this coordinate reference system show the projection for that guy. Okay, so different ni lah. So kalau Tiong kata dia nak buat dia punya projection sendiri, yes you can. Okay, Dr. Tiong, you can make your own map projection. You can have your own coordinate reference system. Okay, right. So when you analyze your data, you always make projection. It means that you don't analyze data using the apa ni? The flat sorry, the sphere earth tu, tapi you have to um, project first the map. So project first or make projection first, baru you analyze your data. So coordinate reference system, again, you know now that there are different types of coordinate reference system. Why there are different types of coordinate reference system? Because there are many methods on how to convert on or how to project a map from earth that is round to flat. Okay, banyak khilaf banyak khilaf. Okay, so the common projection include Robinson, UTM, Universal Transverse Mercator, and Plate-Carré. Okay, right. So and then, all right, we have. Okay, now this is quite important, right? This is important. We also have something that we call as the geographic coordinate reference system. Geographic coordinate reference system. This refers to the locations on the Earth that is round, sphere. For example, WGS 1984. Semua dah pakai Google Map, pernah ada experience pakai Google Map kan? Right? And then if you key in if you, for example, if you go to Google Map and then you look for Pusat Pengajian Sains Perubatan, and you search and then there is a point there, and then when you click what's here at the bottom of Google Map, it shows you you know, for example, like I think this one, when I was conducting a course dekat NIH ni kot. So I search NIH and I found gymnasium NIH, and then you see here 3.1098.101.453. So these are the coordinate reference. These are the coordinates, and these are the geographic coordinate reference system, not um, projected coordinate system. This is geographic coordinate system. Okay, geographic. All right, because these coordinates uh, comes from WGS 1984. Okay, right. So and then you can convert. Okay, you can convert this this value 3.1098.101.4532 from WGS, from you know bumi yang bulat, the earth that is sphere, you can convert to a projected coordinate reference by using some transformation methods. For this one, I use an online transformation or online conversion punya system. So first I select WGS 1984 and I key in the latitude, which is 3.109, and longitude 101.45, and then I can convert this to degrees, minutes, seconds, uh, from 3.109. Actually, it refers to 3 degree, 6 minutes, 35 seconds, nothing, so on and so forth. Okay. So you'd have to remember this. This will not come into exam. Okay. So don't worry. Okay. just to show to you that you can make conversion from the from the decimal from this decimal to degree. Okay, minutes and second. Okay, and then you have one more conversion. Maybe later I'll show you. Okay. Okay, these are the problems with spatial data. Number one, inaccurate and incomplete database. For example, if you want to do mapping for dengue infections in Kelantan lah kan, and then when we want to show distributions or spatial distributions of dengue cases in Kelantan, if we don't have incomplete data, it means that if let's say 20% of dengue cases are not notified, we are missing 20% of cases, right? So distribution of apa ni of spatial distribution will be biased lah, because we are lacking 20% of the cases, right? Let's say lah, let's say we miss all cases in Gua Musang. So when we plot the map, we will we will not have any data on dengue cases in Gua Musang. So when we plot density of dengue or what, it will be zero in Gua Musang. And so it is very dangerous because when people see the map, people will say that, oh, there is no dengue cases at all in Gua Musang. So be careful, okay? So you might have inaccurate and incomplete database. Inaccurate, it means that sometimes when you are rushing or your staff is rushing, they do not calibrate very well um, the what we call that the GIS tools too. Sometimes they go to the location without, and then very quickly they just take the location, and then because of that the location is less accurate. So that's why in some cases the locations fall outside the area. Sometimes it fall into Thailand area. Sometimes they fall on into the sea area. For example, when you go to Bachu area kan, you go to Bachu area, tepi pantai kan, and then your staff geocode, they bring the Garmin tools, and by right, he should wait so that the Garmin can calibrate with the satellite and everything, but he does not wait. He just take the coordinate, so without calibration, so it is less accurate. Sometimes it falls under the sea. So when you map, you see, how come these patients or these patients, the residents or the house are, you know, inside the sea area. uh, Or sometimes when you map um, cases nearby borders in Thailand, I have seen a few data where the cases, when we plot the cases, they fall inside Thailand area. I'm not sure whether they accidentally went into Thailand area ke, ataupun because of the inaccuracy of the coordinates tu. Right. The easiest example is when you tag your location kan. Sometimes you have to wait like 10 seconds, then only the location is accurate. If not, the location can vary by 30 meters or 40 meters kan. So you have to wait like 10 seconds so that your phone will pick up well. And sometimes you have to go out from the house so that the locations is more accurate. Confidentiality. If you know the points of the of if you know the points of the house, then even though you don't know the name, even though you don't know the IC, you can go to their house, right? And if people, if for example, there is rare cases, for example, like maybe rabies ke, like apa lagi rabies or cholera ke, and you have the locations of the house, even though you don't know the name, you don't know the IC, but because of the locations of the house, people will know, oh, this house belongs to person A, right? So the issues of confidentiality, use of zip code ni postcode lah. In Malaysia, the postcode refers to the post office that serve the area. It does not refer to the uh, location of residential address. It refers to the post office that serve the area. For example, Pasir Mas, right? 17,000 17000. So it actually tells us that that postcode is served by pejabat pos Pasir Mas. And usually it has like 10 to 20,000 houses. Unlike in UK where the postcode refers to the locations of the house. And usually you have like maybe 30 or 40 houses here. 20, 40 houses for one postcode. So that's why their postcode are very useful when you want to map data. But in Malaysia, if you use postcode, not very useful. Not very useful. Okay. Geocoding issue, yes, of course, accuracy and locations of uncertainty, overlapping areas and boundaries and whatnot. Okay. So when you analyze spatial epidemiology data, okay, we can do some analysis. For example, we want to evaluate the rates, okay, the rates of of infections between different geographical area. We can also separate patterns from noises. We can identify disease cluster, and we can also study whether there are relationship between the incidence of the um, uh, incidence of certain diseases in the area with some environmental factors or socio-demographic factors and whatnot. So, for example, why in Gua Musang there are more malaria cases? Why those locations have more malaria cases? Is it due to behavioral problem or is it due to environmental problems or whatnot? Why, if you do spatial study for obesity, there are more hotspot in town areas. Is that due to socio-demographic factor? Is it due to economic factor? Is it due to environmental factors? So you can, study the relationship between certain factors with why certain diseases happen in certain locations. Um, but when you want to analyze the spatial data, you have to be careful because the first law of geography says that everything is related to everything else, but near things are more related to far things. This is, the first law of geography by Tobler. So it says that apa-apa yang dekat tu lebih related lah berbanding dengan apa-apa yang lebih jauh. So people that live nearby infected patients people who live nearby infected patients have higher risk of infections. So because of this, the assumptions of certain statistical analysis, especially the assumptions of non-independence, is violated. Okay, so it violates the assumptions of non-independence for traditional linear regression, traditional logistic regression. So you have to have special analysis, not spatial, special or specific analysis to take into consideration this first law of geography, meaning that people who stay nearby are more similar compared to people who are staying further away. You can check this using semi-variogram. Right. When you want to analyze data, you can analyze point data. So, for example, if you have points data, dot, 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 okay? So you can visualize the points, you can plot the locations, and then you can, do kernel smoothing, you can generate point maps, you can generate contour maps, you can generate image map, right? And um, you can also do, for example, this one buffer, right? So you can do buffer analysis for point data, right? Okay. So, and then this is the point dot 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 dot. Okay, and then you can from the point you can uh, generate a point density. You can generate point density map. Okay, so in this map, for example, you can see areas that are that contain higher number, not higher risk, higher number of cases. So and then you can see this red areas. So this usually we call as hotspot lah, hotspot. So because there are more cases in those areas, and then you have yellowish, and then you have green area. So the green is the area that has the lowest number of cases. But again, the question is there are hotspot, two hotspot here, but why these two are hotspot? Is it because the locations are the location contains some risk factors, for example, like carcinogens, or contaminated water, or is it because there are more people there? Because the other areas too maybe not suitable for people to stay. So there are no people outside those areas. People only stay in that small areas here. So you get more cases, right? When you get more cases, you see hotspots. So be careful, yeah. Um, Hotspot doesn't mean that those areas basically areas that have higher risk of disease, but it just reflects that those areas have more people. There are more people there, more dense. Okay. Um, you can also study the pattern of the point. You see this point kan, dot 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 kan. Why those point happen? Okay, does it happen by random? Does it happen by random? Okay, so if it happens by random, it will follow the homogeneous Poisson process. Okay, the homogeneous Poisson process actually is a completely random process. It means that if the disease happen by random, okay, random, secara rawak, okay, then it should follow homogeneous Poisson process. If the patterns is inhibited, okay, what it inhibited means, it means that the distances between points are typically larger than expected for a random pattern. So it means that the those areas are basically have less um what we call has less incidence of diseases. If it is clustered, it means that the distances between points are smaller than would be expected for a random pattern with the same intensity. So we can analyze this using K function, right? So you have this K function here. If you have random, you know, um, terbalik kat sini kan, random sepatut random ni maksudnya, there is no specific pattern, it happens like random. So you can have, um, you know, the, um, the, the, what we call the K function will follow the homogeneous Poisson process. Dekat tengah-tengah, dekat bawah ni kan, the K function. If the disease show clustering, okay, clustering. So when you do K function analysis, you will see that the uh, the K function lies above the homogeneous Poisson process, the blue line. If the disease is less clustered, it is random happen kan, tapi less clustered, it means it's further, which is usually in most situation it won't happen lah. It won't happen like this lah. Okay, it's either random or clustered. Inhibition is like, okay, it rare. It's more rare to happen there. So the K function will lies below the blue line, right? Sometimes you don't have point data. For example, uh, data for diabetes. For example, data for hmm, diabetes, hypertension, or maybe stroke. You don't have points because in Malaysia, uh, most of the time we take points or we geocode data for infectious diseases. Non-infectious diseases we don't geocode, right? So, but we have like, we know that in Pasir Mas, how many people with diabetes, in Kota Baru, how many people with diabetes, in Pasir Putih, how many people with diabetes. So um, because such data is called as aerial data or aggregated data. Okay, aerial data or aggregated data. It is not point data, but it is aggregated data. You know that in daerah or in Mukim, how many has got diabetes, how many has got hypertension, or how many has got stroke. And you can also do some mapping. No, you can do mapping like this. Like for example, Hulu Selangor 66 something, dengue fever kan. Gombak 73, Petaling 66. So you can also plot data, and this is called as aerial data. Right. And then you can plot choropleth, not chloropleth, choropleth, bukan Clorox juga, choropleth maps or dot density map. Cumanya aggregated or aerial data ni is biased when you have large study region. For example, if you plot Malaysia lah kan, the obvious state would be Sarawak, Sabah and Pahang, right? Perlis is very small, right? So you tend to see, I mean, Sarawak and Selangor and Pahang will always tend to be, like more interesting for people to see lah because dia besar kan. Nampak kan? And boundaries problem and difficult to visualize highly skewed distributions. And then so we have point data, we got aggregated data, we also have continuous data. This one is raster data lah, rainfall, humidity, air pollution. You can also, if you want to analyze this, you can summarize data by area. You can also plot using choropleth or proportional maps. For example, this one lah, a choropleth map of the New Haven census tracts. This shows case fatality ratio for 2013-2016 Ebola epidemic in West Africa, right? So, okay, this is not a continuous map. This one continuous map. This one is basically, again, choropleth map. Right. Right. So this is an example of a continuous map or raster map. This is estimated malaria prevalence. Malaria prevalence. Maria pula. Okay. Malaria prevalence. Estimated dengue outbreak in Brazil. So sebenarnya dia orang tak ambil data for each location ni. Tak mampu sebenarnya. What they did is basically they took data from this like randomly. Tak random pun tak apa sebenarnya. They took data from maybe 100 locations, maybe dot. And then after that, they did geostatistic analysis. And after that, they make prediction. Kan? We learned yesterday about prediction. So they make predictions to predict areas that are not uh, in the area that were not recorded, because they only record areas or data from 100 areas. For example, like this area, this kampung, this kampung, this kampung, this kampung, so 100 villages. But because they can make prediction, then they can create the estimated malaria prevalence for all over the country using 100 points of data. Okay. So ni dekat mana ni? This is not sure which country this one. In Brazil, Brazil. This one Brazil. This is dengue outbreak in Brazil. This one don't know which country, Okay. So so when you want to analyze spatial data, um, you can you can do spatial point pattern analysis if you have point data. You can do interpolation and geostatistics. You can do aerial data and autocorrelation, and you can do disease mapping. So it depends. It depends. So you can do spatial point pattern analysis. You can analyze interpolation and analyze geostatistics data. You can also analyze autocorrelation, and you can also analyze the disease mapping. Spatial clustering. Okay, clustering is spatial aggregation of disease event. Disease is clustered if there is residual spatial variation in risk after known influence have been accounted for. So that is statistician punya ayat lah yang tu tak faham tu kan. Okay, but we know that, okay, residual spatial variation in risk after known influence have been accounted for. Okay, tak apalah, okay. Clustering for spatial point data. I mean, we can do clustering analysis for point data, but if you have aggregated data, we can also do spatial clustering for aggregated data. Tapi of course, spatial clustering for point data is much better lah. So we have two types of spatial clustering, local or global, right? Global clustering, when clustering is apparent throughout the study region. Local clustering, when cluster detection define the location and the extent of the clusters. Global clustering is when cluster happen, throughout the region. For example, ada cluster seluruh Malaysia kan. Tapi kalau local clustering ni local cluster yang happen maybe in Kelantan saja or in Sarawak saja ke, so that is local clustering. Satu lagi analisis yang kita boleh buat ada spatial variation in risk. For example, this map kan, spatial variation of risk for prime age adult women mortality. So they compare mortality between male and female. So cumanya I'm not sure whether they compare antara male versus female or female versus male. Sorry, dekat sini ada men and women. But for what is this? For what is this? Let me check. Hmm. Not sure. Tapi dekat sini what they did is basically they can measure the risk and they can map area where is the area that is above 1 or where are the areas uh, where the risks are below 1. So area that have risk below 1 is considered as areas that have lower risk for certain disease. Areas that are above 1 shows that those areas are basically have higher risk for certain diseases. Okay. So mortality. So in this area, it shows that for men, the red area shows the area where mortality are higher. Compare mortality are higher, and this is for women. The red area basically shows area that have higher mortality for women. Right. Okay. Yang ni kan, if you want to do this one, imagine if you want to study mortality, perinatal mortality lah, for example, right? So perinatal mortality. So you go to all hospital in let's say like you study Kelantan, Terengganu, and Pahang. So you go to each hospital, you geocode the hospital, and then you take information about prenatal mortality, for example. So, or maybe even better, you go to each klinik kesihatan. Okay, so I'm not sure how many klinik kesihatan in Kelantan lah, how many kan. So, from each klinik kesihatan, you take the mortality rate, prenatal mortality rate, for example, and then you can make a map like this. Which area have higher risk for prenatal mortality and which area have lower risk for perinatal mortality. Very useful. So, all right. And this is the Plasmodium falciparum infection. Okay. Um, so this comes from geostatistics analysis. So they created a spatial variation map after they adjust for covariate, certain covariate. So they show which area have risk above. This is one. This is this. This is probability. I think probability of no. This is log. Bad net coverage levels were independent associated with the reduced risk of plasmodium falciparum. Right. So in this area, what they did in this study, what they did was they took data from certain numbers of area. They went to the kampung lah in this area kan. I think not sure which country this one. So they take information about the bad net coverage. Okay, kampung ni what is the bad net coverage? Kampung ni what bad net coverage? Kampung ni what bad net coverage? and they at the same time they measure the number of Plasmodium falciparum infection. Okay, they also measure the Plasmodium falciparum infection, and also they got the coordinates of the kampong, the coordinates of the villages. So they did geostatistic analysis. After that, the coverage include bed net coverage and so on and so forth. They can produce, or they produce the map of the um, risk of Plasmodium falciparum for this country. So it doesn't mean that you have to go here, you have to go here, you have to go there. No, no, you don't need to do that. You just identify maybe 100 villages or 200 villages or 100 klinik kesihatan or 200 klinik kesihatan, or you do 100 or 200 apa ni camp kesihatan, and you ask people to come in and then you take blood kan. Then that the location of the klinik kesihatan or the camp kesihatan, you take the coordinates of the camp kesihatan, and then from there you can make this plot. It's something that is can be done, you know. I think a few people dekat NIH, IMR especially dah buat, tapi it's not a very commonly used study in Malaysia. But if you can do this, this is quite interesting, yeah. Uh, Because my I before this always I thought that we have to go to all this area kan. Maksudnya we have to go there, here kan. So it means that we need to cover like maybe 20 to 30,000 places. No, you don't have to do that. You just cover like maybe 100 to 200 places, get the coordinates, do some screening there, and then you can make prediction. And then from that prediction, you can create this spatial variation map. I think yeah, I think Dr. Kusaifullah did this, okay, geostatistics. So I think maybe I can look at his paper and how he did uh, analysis for similar to like this. Right. So in summary, spatial data contains coordinates. Spatial data contains coordinates, latitude, longitude, X or Y, and there are different types of spatial data: points, spatial data, polygons, lines, raster. And then, tiba-tiba ada shapefile kat sini kan. The most common format lah for spatial data is that shapefile format. Okay. And then try to understand also the coordinate reference system. There are different types of coordinate reference system. We mentioned just now WGS 1984. In Malaysia, the common coordinate reference system, the geographic coordinate reference system, is still WGS 1984, but the projected coordinate reference system, I always find Kertau RSO Malaya meter. I'm not sure why Kertau RSO Malaya meter. Kertau RSO Malaya meter was created in 1984, tahun 48 masa tu, oleh penjajah-penjajah Mak Saleh lah. Because I asked this when I was in UK, Lancaster. So I met one of a guy that is doing a lot of spatial packages for art, for QGIS, and also he went to Google punya apa ni um, uh, offices lah. So I asked him lah, okay, why? I mean when I make projection right from WJS to Kertau RSO Malaya meter, the coordinates shifted for about 100 meter. You know, okay, when when there is this is a sphere, right? Then WGS 1984. Now I need to convert to Kertau RSO Malaya meter. And when I converted, the points shifted about 100 meter. So I asked them lah, I asked him, so why, every time I convert, the points shift for about 100 meters. So he said maybe there was, some kind of miscalculation in 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 uh in the formula lah, because all these are basically mathematical formula, no. So yeah, so that's the problem, um and then understand projection. What is WGS 1984? What is Kertau RSO Malaya meter? I think the latest one, or the one that our government recommends, is GDM 2000. Bukan gestational diabetes mellitus, okay? GDM 2000, the name of the projected coordinate reference system. But I'm not sure why DOSM and YKKM still use Kertau RSO Malaya meter. I'm not sure why. Okay. Right. So when it comes to analysis, you can do point pattern analysis. But if you don't have points data, you can do aerial data analysis, um, which is or are suitable for MPH. But when you go to the RPH, you may want to do geostatistics. Okay, for example, INLA, integrated nested Laplace approximation, to so that your analysis will be more valid. Because why? We can't do linear regression. We can't do logistic regression. Um, because both analysis requires independence assumptions. But you know that spatial data, they are not independence. Those who stay nearer have higher risk for infection again. So that's why you need to use analysis that consider um, this special feature, the Tobler law number one, which says that everything that is nearer have a higher similarity, something like that lah. Okay. And then last one, you can also do risk mapping. There are some wonderful app packages where you can uh, you know uh, draw some map, and at the same time you can show which areas that have higher risk for infection, which areas have lower risk for infection. So if you want to read more, you can go to Paula Moraga Paula's website. There is a link for open book, the geospatial health data modeling and visualization with R, Inla, and Shiny. I think Paula just published the second version of her book for this one when I met her last time. Um, and also, I think she also published another book lah, if I'm not mistaken. So, but the books are available online. But again, tapi it always feel better lah. It feel nicer to hold the real book rather than the online book. Kan. Okay, so if you want to do practical, you can go to Epidemiologist R Handbook. Also very easy to follow, very useful. The epirhandbook.com. And Robin Lovelace um, also has a wonderful book, Geocomputation with R. I think Robin Lovelace is more to like doing mapping, but Paula is more to analysis, like how do you more so Paula's book is more to applied. Robin Lovelace book is more to like mapping kind of book lah. So yeah, and I think Robin Lovelace use a lot more T-map package. Okay, T-map package. And to apa dia? An introduction to spatial data analysis and statistic course in R. Yeah, you can also go to that spatialanalysis.org. Also very useful, very basic for data visualizations. But if you want to do more analysis, a more in-depth analysis, you definitely has to read R in La book by Paula Moraga. Okay. So I think yeah, that's all. Our lecture today. It's always sleepy lah when we are not doing any practical kan. So so but you have Dr. Afiq and Dr. Hazlino to help you with, so they can help you with some hands-on or practical with R. But if you maybe after exam ke, if you want to do some practical on spatial data analysis, just let me know lah. Alright, so any question? So kita stop recorder.